Yeah, all we have to do today is answer this question of for which values of n are regular n-gons constructible. That was what we were doing last time. By the way, I lied to you about something. I was reading a bit. I told you the ancient Greeks, they could construct 3, 4, and 5 gons, regular 3, 4, and 5 gons, and then all powers of 2 multiples of that, right? Apparently they knew how to modify the construction of a 3 and a 5 gon to get a 15 gon as well. So they could do a little bit more than I thought. But then remember, they couldn't do 17 gons. That was Gauss came along, 18 years old, 1796 I believe, showed that a 17 gon was constructible. Didn't provide the construction, someone else did a few years later. But yeah, the question is, what regular n-gons are constructible? And it turns out it's sort of deeply rooted in number theory. So let's make a definition here. A Fermat number. This is the same Fermat as we discussed earlier in the semester. Did a whole lot of number theory. Of course, the famous one is Fermat's last theorem that we talked about, so Pierre Fermat. A Fermat number is a number of the form f sub n is going to be 2 to the n, 2 to the 2 to the n plus 1. All right, so what are the first few? So the first few, I should tell you what n is, right? N bigger than or equal to 0 is an integer. So a natural number if you want. The first few Fermat numbers are f naught. F0 is 2 to the 2 to the 0 plus 1. What does that equal? 3, right? 2 to the 1 plus 1 is 3. F1 is 2 to the 2 to the 1 plus 1. That's 2 squared plus 1 is 4 plus 1 is 5. F2, 2 to the 2 to the 2 plus 1. 2 to the 4 plus 1, 17. F3 is 2 to the 2 to the 3 plus 1. 2 to the 8, what's 2 to the 8? 256 plus 1, so 257. F4, I'm still going for a reason. 2 to the 2 to the 4 plus 1. You'll remember these from last time. Remember I said Gauss could construct a regular 17 gon. A little while later, early 1820s, someone came along and constructed a regular 257 gon. I gave you one more. Some guy gave a 100 long page construction of a 65,500 and I think it's 37 gon. The next one I'll list, this will be the last one I list, F5, 2 to the 2 to the 5 plus 1 is 429, 496, 7297. Let's put the commas in the right spot. Here, here, here. Fermat numbers are really well studied. You can prove things, for example, like they always end in a 7, except for the first two. What else might you conjecture, though? You might conjecture that they're always prime. And these look like prime numbers. In fact, this is prime, this is prime, this is prime. You can check 257 is prime, and this one wouldn't take you too long. 65,000, you can check it's prime. Then you get to here, this is pretty big. What's this, 4 billion and something? You can check, if you check it. Fermat himself was unable to factor this, although he knew enough about number theory that he should have been able to. Most people think the reason he couldn't factor it is because he made a mistake in his calculations. So this is actually not a prime number. This is composite. So these first 5 here, these are prime. And this guy, not prime. It's divisible by 630 something, I think. I didn't write it down. And so, of course, if you're checking it by hand, checking up to the first 600 divisors is kind of painful. But it's not prime. The first 4 are. And these have been checked. Out to n equals 32. And f sub n for n between 5 and 32 are not prime. Why haven't we checked more of them? They're gargantuan numbers, right? F sub 32 must be a very, very, very huge number. There's probably less particles in the universe than however big that number is. So they're known to not be prime, and it's conjectured that these are the only ones. So, a Fermat prime is a prime Fermat number. I'm lying to you a little bit here. If you want to be really precise, the actual definition is it's a prime with the form 2 to the k plus 1. But you can prove that the only way this is prime is if k is of the form 2 to the n. All right, so all Fermat primes must actually, by this definition, you can prove a number of theoretic reasons that all Fermat primes must actually be Fermat numbers. So I'm lying a little bit just to make the definitions easier. And the conjecture, F0, which is 3, F1 equals 5, F2, which is 17, F3 equals 257, and F4, which is 65, 5, 37, are the only Fermat primes. Remains unresolved. No one really knows if this is true. We don't even have a whole lot of evidence that it's true. We've only checked the first 32 of these things. But there's the conjecture. And now come into the answer for our question, this is which n-gons are constructible. So if you just called this the Gauss's theorem on constructibility or something, everyone would know what you're talking about. If you want to be very formal and precise, it's the Gauss-Wanzel theorem. Going back to 1837, that fully answers our question. And it says this: a regular n-gon is constructible. And of course, I mean constructible by definition means with a compass and straight edge, but I'll put here for completeness anyway. With a compass and straight edge if and only if n is of the following form. If and only if n is 2 to the k times m. Where k is an integer bigger than 0. So that part's not very interesting. I know if I can construct a regular n-gon, then I can construct 2 to the k times that n. But what is m? Well, where k is a natural number, and m is either equal to 1 or any product of distinct Fermat primes. Is a product of distinct Fermat primes, or equal to 1. Is sort of think of that as taking no Fermat primes at all. Then you just have 1. Alright, so this is why, for example, I can construct, or Gauss could find a construction for a 17-gon. Just take the Fermat prime 17 times 2 to the 0. But you can't construct a regular 9-gon, because 9 is not a Fermat prime. 3 is, but I can't do 3 times 3 because it says to be distinct Fermat primes. It's also why you can construct a regular 15-gon. You can take 3 times 5 times 2 to the 0. So what does this mean? This means if you remove these sort of multiples of 2, which are easy, then there's only a distinct number or a finite number of different products of Fermat primes, right? At least that we know of. There might be more, but so far these are the only ones that we know. Why the Gauss-Wanzel? I believe so. Gauss constructed his 17-gon in 1796 when he's 18, 19 years old. I believe it was a few years after, I think maybe 5 years after, so about 1801, he proved that this was a sufficient condition. So if n was of this form, then you could construct it. He also went ahead and claimed it was a necessary condition, which is the whole theorem here. It's sufficient, necessary, and sufficient. But he didn't provide a proof for the necessary part. I think a lot of people took him at his word, but it wasn't until 1837, so quite a while after, that this guy, Pierre Wanzel, came along and he proved the necessary part. And this completely answers our question of which regular n-gons are constructible. Well, if they're of this form. Kind of interesting, the connections in mathematics, right? I'm sure when Pierre Fermat was studying Fermat primes, he had no idea he was studying anything to do with this would ever have anything to do with compass and straight edge constructions. But again, these answer questions that are thousands of years old in mathematics. Any questions about that? All right. I want to provide you with one more construction. It's the construction of a regular pentagon. The ancient Greeks knew how to do this. Euclid provides a construction in the Elements. So let's just go through a construction of a regular pentagon. We've already talked about how to construct a regular triangle, equilateral triangle, how to construct a regular quadrilateral, a square. Pentagons are more complicated, and there are lots and lots of known constructions. And you're usually trading off, in the constructions, you usually trade off the complexity of the construction itself. The more complex the construction tends to be, the easier it is to prove that you've actually constructed a regular pentagon, versus the simpler the construction tends to be, the harder it is to prove that this actually works. I haven't looked too closely at the way the textbook does this, but it looks like it's a slight modification on what we're going to do. Ours is owed to a Japanese mathematician somewhere in the late 1800s, I believe, and it's very similar to the textbook, but here's the solution. First thing, anytime you're trying to construct something regular, you tend to start with a circle and just choose evenly distributed points around the boundary. So, let's construct a circle, draw a circle rather. There's no real construction there, you just take your compass and draw it. So draw a circle. We're going to construct its center. Construct its center. And also let's construct two perpendicular radii. Let me give it center name. Center O, and construct two perpendicular radii. So here we go. I've drawn my circle. I go ahead and I construct its center, which we always can do. I draw one radii, well, one radius. And then all I have to do is come into the center here and erect a perpendicular, let's say this one. So let's actually give these radii names. Construct two perpendicular radii, OA and OB. OA and OB as shown. All right, what now? Now a lot of constructions start this way. Let's go into OB and construct its midpoint, M. So 2 is construct the midpoint, M. And I'm going to draw the line AM with my straight edge. And draw AM. All right, next up, come into M, and we'll draw a circle centered at M, passing through O, which of course means it also passes through B. So I'll just draw the upper half of it, we don't need the whole thing. So we'll draw the circle centered at M, passing through O, and it's going to intersect AM at T. Draw the circle centered at M, passing through O, and let T be the point where it intersects AM. And I've gone with this because this is actually one of the easier constructions. There's only one more thing I need to do now, which is come to A and draw a circle centered at A passing through T. So circle centered at A passing through T. Draw the circle centered at A passing through T. And the 2 points where this circle meets the boundary, not the original circle, not the boundary, but the actual original circle, let's call those points P1 and P2. Let P1 and P2 be the points where this circle intersects the original circle. My claim is that that's all I need. Now we're essentially done with the construction. My claim is that P1 to P2 is one side of a regular pentagon inscribed in the circle. Which means I've technically done a little bit more, right? P1 to A to P2, those are two sides of a regular pentagon, a regular decagon. So P1, P2 is one side of the inscribed regular pentagon. Can you see that that's all I need to do? Can you see how to get the other sides? I'm going to cheat a bit. Because I don't want to write a whole bunch more. Step 5, I'm just going to say repeat in the other quadrants. You really wouldn't do this, but I don't want to write more. So repeat in the other quadrants. You have to be careful about which midpoint you're choosing and so on. This isn't really how you would construct this. The actual construction is simpler. All I have to do here, if I want another side, come into P2, draw a circle centered at P2, passing through P1. That's going to give me a circle that intersects somewhere down here. And that would be another side. Okay, and then I would take a circle centered at this point, passing through P2. That would give me another side. But I think that's obvious enough that we can just sort of end this construction here. So what's the catch? Well, here's the construction, but just because we've made this construction and I've given you these steps, there's nothing in here that makes it obvious to me that yes, I've constructed a regular pentagon, right? In other words, if this was a regular pentagon, then this angle I've constructed would have to be 360 over 5, 72 degrees. There's nothing that makes it obvious to me that I've constructed a 72 degree angle, right? So we need to prove this, and I'll be honest, I'm not going to give you full proof because it's longer than I think it's worth, but I'll get you halfway there. So proof, and we're proving that this constructs a regular pentagon. All right, so my picture is a little bit messy at this point, but OA, let's call OA, let's just call it R. It's the radius of the circle, so we'll call that length R. Let OA equal R. Then how long is OB, or sorry, how long is OM? What's the length of OM?
R over 2.
R over 2, right? OB is another length R, so M being the midpoint, that's R over 2. Let OA equal R. Then OM is R over 2. And that implies that AM, well, use Pythagoras, this is a right angle, so this is a right triangle, sides R and R over 2, this would be the square root of R squared plus R squared over 2 squared 4. That is square root of 5R squared over 4, so R over 2 times root 5. So what's AT? I want the length of AT. Well, that would be AM minus MT, right? So this is AM minus MT. We just computed AM. This is R over 2 times root 5 minus, what's the length of MT? Yeah, it's the same as OM, and OM is R over 2, right? Why is it OM? Because it's just another radius of the same circle. So this is R over 2. So this is R over 2 times square root of 5 minus 1. And last but not least, T, AT, is just a radius of the same circle as A to say P2, right? So A P2 is AT, so that's R over 2 times the square root of 5 minus 1. And here's the part that I'm going to skip. But now, if you were to inscribe, if you were to take a inscribed regular tengon, so inscribe a regular tengon, so this is 36 degrees, and you measured the side length there, you would get exactly this length. All right, so I'll just tell you this is a fact. You can do the trigonometry if you want. The side length of a regular tengon inscribed in a circle of radius r is given by, let's just say is, r over 2 times square root of 5 minus 1. Not too hard to do. You would just sort of, you construct the midpoint here, you drop the apothem, you do a bunch of trigonometry on these right triangles. A right triangle with one angle being 18 degrees. You'd have to compute sine of 18 degrees. 18 is 90 divided by 5. You do a bunch of trig with double and triple angle formulas. There's a whole lot that goes into it, but you can eventually show that the side length is exactly equal to this. And that's the part I'm going to skip. I don't think that trig is worth doing. But that's it. Once we have that this side length is given by this guy, then what we've actually done here is we've constructed a regular tengon, and we've just taken alternating points to get a regular pentagon. So hence, we've constructed a regular tengon and chosen alternating points to extract a regular pentagon. And that's it. We'll stop here with that. If you're curious, the textbook does go on. I believe there's a 6F. What are we on? 6E is constructible numbers. It says quite a bit more about constructible numbers, by the way, if you want to read that. 6F is, he calls the section changing the rules. And the way he changes it is he allows, okay, I have a compass and straight edge, and I'm allowed to make a mark on my straight edge. So now it's a ruler. And if you change the rules in that way, then these constructions are no longer impossible. Now you can square a circle, now you can double a cube, and so on. So that one little change really changes what you can construct, which numbers are constructible. And like I said, for a long time, the ancient Greeks, they just thought these were hard problems. They didn't realize they were impossible. And still to this day, a lot of people don't realize what impossible means. It's not that we haven't found a construction, it's that you cannot do it. So you still see incorrect constructions being submitted all the time, and those incorrect constructions pretty much almost always feature some sort of rule breaking. Right? The other way they could be wrong is they're just straight up wrong, but usually they've got some sort of rule breaking where they've essentially created a ruler instead of a straight edge. But yeah, that's geometry. Hope you guys enjoyed it. Geometry 2 next semester, if you're taking that with me, that should be a lot of fun. It'll feel a little bit different than this. We'll still do proofs of this nature, but we're going to take a very axiomatic approach to different geometries. And yeah, the exam's on Friday. No, today is Friday. The exam is tomorrow, Saturday. And not just 24 hours this time. Again, I open it up to the whole weekend, to Sunday as well. Should feature 2 construction problems and 2 problems from the rest of the semester. And Any questions about it? What did I want to say? Oh yeah, and you have a homework due tonight. I'll post up solutions immediately at midnight, so the moment they're due, so that if you wanted to get started on your exam straight away, if those solutions help you, then yeah, they'll be there. All right, thanks a bunch, guys, and take care.